Ephemeral Diffie-Hellman key exchanges, abbreviated in this course as DHE, allow two interacting entities, such as Alice and Bob on this slide, to commonly agree on a symmetric encryption key K, without this key K ever being on the wire between Alice and Bob, neither in plain nor encrypted, as it was the case with the hybrid encryption scheme discussed in the previous lesson. In order for this to work, it's assumed that Alice and Bob, by following a certain protocol, have agreed on using a set of Diffie-Hellman parameters G and P, which are public knowledge available to everyone. Barring few technical constraints, these Diffie-Hellman parameters G and P are simply prime numbers, with the prime number P again in the order of at least 2048 bits. If Alice and Bob now want to derive a symmetric key K that they can subsequently use to encrypt the data exchanged between them, then both Alice and Bob, in a first step, each completely by themselves, create a secret random number that each of them will keep private. Let's assume the random number Alice creates for herself is X, and the random number Bob creates is Y. Then Alice calculates the power of the public Diffie-Hellman parameter G to X modulo P and sends the result to Bob. Bob does the same with his private number Y, calculating G to the power of Y modulo P and sends the result to Alice. The values that Alice and Bob exchange in this manner are referred to as half keys. Based on these half keys, both Alice and Bob can then again, each completely by themselves, calculate the symmetric key K in isolation. Alice, for example, takes the half key B received from Bob and calculates this half key B to the power of her secret X. Looking at the arithmetic, this results in the value G to the power of YX. Bob does a similar calculation based on his secret Y, and looking at the arithmetic involved, we can see that Alice and Bob indeed arrive at the same value, which they then can take as a symmetric key to encrypt the data later exchanged between them. To repeat, the advantage of this is that the symmetric key K is never on the wire, neither in plain nor encrypted, and that if possibly one day such a secret X or Y of Alice and Bob would leak, only the one corresponding key K could be calculated, and with it only the data related to this specific session could be uncovered. This security guarantee is now generally referred to as forward secrecy. Now, calculating the symmetric key K is easy and efficient once either X or Y are known. Given that Alice and Bob exchange half keys which both have the X and Y somewhat embedded within them, the security of these Diffie-Hellman key exchanges rely on the assumed difficulty of calculating discrete logarithms. This, again, is only assumed to be difficult, and no publicly known algorithm exists to calculate these discrete logarithms efficiently, at least for classic computers. Under the existence of quantum computers, this looks different, but a few words on this on the next slide. All in all, what you see here on this slide is the classic ephemeral Diffie-Hellman key exchange providing forward secrecy and the nowadays accepted solution to the problem arising from the use of hybrid encryption schemes. A modern version of the ephemeral Diffie-Hellman key exchange presented on the previous slide is the ephemeral elliptic-curve Diffie-Hellman key exchange, fortunately coming along with an abbreviation ECDHE. At this point, I will omit a detailed discussion of this ephemeral elliptic-curve Diffie-Hellman key exchange, as the mechanics of this key exchange are the same as the mechanics of the classic ephemeral Diffie-Hellman key exchange discussed on the previous slide. The difference between these two key exchanges is, as the name indicates, that the elliptic curve variation now operates on mathematical entities known as elliptic curves. The assumed to be difficult problem for ECDHE is then also not just the plain discrete logarithm problem, but the discrete logarithm problem for elliptic curves. Broadly speaking, the reason elliptic curve-based cryptographic primitives are gaining in popularity is the fact that many of these primitives achieve the same level of security with much smaller keys involved. The classic ephemeral Diffie-Hellman key exchange, for example, involves numbers with lengths in the order of thousands of bits, whereas the elliptic curve equivalent involves numbers in the order of hundreds of bits. I close this lesson with an important side note related to the security of both the classic ephemeral Diffie-Hellman key exchange as well as the ephemeral elliptic curve Diffie-Hellman key exchange. The security of both variations relies on the assumption that the discrete logarithm problem on the respective mathematical entities are difficult. This is currently assumed to be the case for classic computers. However, for quantum computers, fast algorithms exist to calculate these discrete logarithms. As such, and as it was also the case with RSA for asymmetric encryption, it's important to be aware of this insecurity of Diffie-Hellman key exchanges in presence of sufficiently strong quantum computers and to adopt a migration plan to replace both key exchanges, DHE and ECDHE, with post-quantum cryptography algorithms resistant to quantum computers.